Alright, lecture 2.8, which corresponds with section 3.7 from the textbook. This is the very last lecture for Unit 2, guys. So after you're done with this lecture, you are ready to rock and roll with the test review and take the test 2. But before we get to inverse functions, we need to discuss the property of being one-to-one and what it means for a function to be one-to-one. Basically, a function is one-to-one if matching outputs implies matching inputs. So in other words, outputs are unique. So there's one input which corresponds to one unique output. And thus we can use the horizontal line test. The horizontal line test determines if a function is one-to-one, and we know a function is one-to-one via the horizontal line test if no horizontal line intersects the graph more than once. So let's go ahead and practice with that horizontal line test. So we got some functions here. Let's determine if they're one-to-one. Now these, if you recall, is just a bunch of transformations. Talked about these 2 lectures ago. Recall, transformations don't change the core characteristics of a function. So go ahead and pull out that library of functions sheet that was posted earlier. Feel free to pause if you need to. And if we look at that, we can see that this is a square function which is going to be shaped like a parabola. So this function is going to have this shape, and we can see it fails the horizontal line test because a horizontal line test is going to hit it more than once. So this is not one-to-one. If we look at this function in example 2, this is a cube root function which is shaped like this, and we can see no horizontal line is ever going to hit it multiple times, so it passes. So the cube root function is one-to-one. Now let's look at the absolute value function. This is on the back side of that library of functions handout, shaped like a V, and this is clearly not one-to-one because a horizontal line will strike it more than once. So this is not one-to-one. So with the with the horizontal line test, it's very easy to determine if a function is one-to-one. Now a function must be one-to-one in order to have an inverse function, which we're going to go ahead and define now. So let f be a one-to-one function with domain x and range capital Y. Then the inverse function is going to flip that domain and range. And basically what the inverse function does is it inverts all the inputs and outputs. So keep in mind a function is input-output. So what's the opposite of input-output? That would be output-input. So everything about inverse functions is summarized in this diagram. The function f maps x to y, then the inverse function is going to take that y value and revert back to the original x value. So it just switches your x's and y's. So it switches your inputs and outputs. And you'll see why we need to have this one-to-one property. Let's go ahead and look at this. So here we have relation f, which maps 1 to -5. And here we're looking at example 1. It maps 1 to -5. 2 to 0, 3 to 2. So the inverse is just going to reverse all of those. Now, is f one-to-one? Well, 1 maps to -5, 2 maps to 0, 3 maps to 2. Everything's unique, so yes. And you can see the inverse is a function because if we look at the inverse relation, -5 maps to 1 and nothing else. 0 maps to 2 and nothing else. 2 maps to 3 and nothing else. So it is a function. Now let's compare that to example 2. When we invert it, we can see g is not one-to-one because 1 maps to 5, but 3 also maps to 5. It's not one-to-one. If we were to plot those points, they would fail the horizontal line test. And you can see those repeating outputs, when we invert, become repeating inputs, which means the inverse is not a function. So you can see why, if an inverse function is to even exist, it must be one-to-one. If it's not one-to-one, then you have repeating y values. And when you invert, those repeating y values become repeating x values, and thus you will no longer have a function. So it's very important that the function is one-to-one in order to have an inverse function. It'll have an inverse relation, but in order to have an inverse function, it must be one-to-one. So let's do some more examples here. So f f at 1 is 6, f at negative 3 is 10, f at 2 is 5, evaluate. So the inverse of 6 is 1. All you're doing there is really switching the x and y. F inverse of 5 gets you back to 2. F inverse of 10 gets you back to negative 3. Now you want to be very careful at f inverse of negative 3. So we want to look for a y value of negative 3. There aren't any, so this is actually undefined. Now, throughout mathematics, we use inverses when solving. That's because inverses tend to cancel, right? The inverse of addition is subtraction. We use that to cancel. If we want to cancel multiplication, we use its inverse division. If we want to cancel a square root, we use its inverse squaring. And inverse functions have a similar property. So functions f and g are inverses if and only if, when composed together, they cancel. So if they're inverses, if I take g and put it into f and it cancels, and I put f inside of g and it cancels, then those have to be inverses. And note the if and only if. It's the biconditional. If they cancel each other, then they must be inverses. If they are inverses, then they must cancel each other. The biconditional works both ways. So we can use that to prove if two functions are inverses. So we're going to do that in this next example. Let's prove that these two functions are inverses. And we'll begin by looking at f composed with g at x. So that's f at g at x. So we want to work from the inside out. G at x is negative cube root of x. We're going to take that, put it into function f, which is input negative of the input cubed. So the cubing cancels the cube root, and we got negative of negative x, which is x. So f cancels g. Let's see if g cancels f. So that'd be g at f of x. So that's going to be g at negative x cubed. So that's going to be the negative of the cube root of negative x cubed. And that also equals x. So, yes, they are inverses because they cancel each other. So it's going to wrap up by coming up with a strategy for how one can determine the inverse function. And basically, it's switch the x and y. That's what an inverse does. It switches the x's to y's and the y's to x's. So we'll just do that algebraically. Switch the x and y, solve for y, revert back to function notation when you're done. So we mentioned several lectures ago that this function notation is interchangeable with y. And we're going to go ahead and invert, so all your y values become x values, all your x values become y values. And there we have the inverse. We just got to put it in explicit form. So we talked about explicit form a few lectures ago. It's basically get y by itself. So you can add 3 to both sides. Divide by 2. And there we have it. So there is our inverse function. So that's the inverse of g, which is denoted as such. It's x plus 3 over 2. All done. Let's look at the next example. So this is the function of y equals the 7th root of x minus 8. Well, switch the x and y. So there's our inverse. So what we want to do now is go ahead and get y by itself. So we'll raise both sides to the 7th power, canceling that 7th root. Then add 8. So that's the inverse of f. F inverse is x to the 7th plus 8. So these last two examples demonstrate what I call intuitive inverses. If you look at example 1 with function g, the inverse of 2 times x minus 3 is, well, x plus 3 divided by 2. Makes sense. You know, the opposite of minus 3 is plus 3, and the opposite of times 2 is divided by 2. We can kind of see that in example 2 with function f. You know, the 7th root of x minus 8. Well, instead of minus 8, we have plus 8. Instead of the 7th root, we have a 7th power. So these two examples demonstrate what I refer to as intuitive inverses, right? So you could probably guess these. But you need to exercise caution because sometimes the inverse can surprise you. Let's look at example number 3. So you might think here, well, I'll just switch it around perhaps, but this one's not as clear. So what you need to do is go ahead and invert it. So switch the y to x and the x to y. So there's our inverse. And let's go ahead and solve it. I'm going to multiply both sides by y plus 1. And again, I want to get y by itself, so let's go ahead and distribute here. Again, I'm going to get y by itself, so I'm going to get all my x's on one side, all my y's on the other side. So I get xy minus y equals 3 minus x. And this goes back to test 1. We're trying to get y by itself. Note that y is in two terms that don't combine. Remember, if your variable of interest is in multiple terms that don't combine, try factoring it out. And divide accordingly. Alright, there's our inverse function. So the inverse of h is 3 minus x divided by x minus 1. And as you can see, not going to be able to really guess this one. This one's a bit trickier. So you just got to be careful. Sometimes inverses can surprise you. You just got to switch the x and y and see where it takes you. Alright, well that's a wrap with Unit 2, guys. We are done, so feel free to start working on that test review, and have a wonderful day.